Hello and welcome to Analog Electronics and Physics Lecture 38, the video version. Analysis of RLC circuits is the topic for this time. So, contents, reminder of the general form of frequency responses, and then go on to look at these RLC circuits, which are circuits which contain a resistor and an inductor and a capacitor, usually in series. This configuration can lead to the phenomena of complex poles, and I want to spend some time in this lecture looking at what complex poles mean and what they actually do. So, start off with an analysis of the general form. Now, the general form we've seen a couple of times before now. The gain at low frequencies is G times j omega to the power of n. Low frequencies here being defined as frequencies at which all of the other terms in these zeros and poles here can be approximated to be 1 because the omega is much smaller than all of the z's, and the omega is much smaller than all of the p's. Net result, all you do is end up with h of omega is approximately equal to g times j omega to the power of n. We have this. Now, when you don't have any zeros at 0 Hertz, n is 0, so we just get that, g, and the gain at low frequencies is just given by this term g. However, when we do have some zeros at 0 Hertz, the gain at low frequencies, we have to approximate that as g times j omega to the power of n, where n is the number of zeros at 0 Hertz we have. All of the circuits we've seen so far, if they have any zeros at 0 Hertz, they only have one of them. So we can say for a circuit with 1 zero at 0 Hertz, the response at low frequencies is approximately equal to j omega g. Anyway, that's the kind of thing we've seen before. Moving on. An example of an RLC circuit. Well, once again, it's a potential divider. It's fairly straightforward to determine what the frequency response of this circuit is. We can just apply the standard potential divider equations. In this case, V out over V in is the impedance of this term here, 1 over j omega c, divided by the total impedance in the network, which is j omega c plus r plus j omega l. And if I multiply through by j omega c, every term top and bottom, I end up with this. Here we have a single 1 in the numerator, which means there are no zeros in this response at all, but I have in the denominator a quadratic. The biggest power of j omega is 2, and that means that I've got here 2 poles. The question is, what frequency are those poles at? And what do they do? Well, if you have 2 poles like this, we have a quadratic expression in the denominator. To find the poles, we can proceed as follows. Just equate the denominator that we have with the standard form for 2 poles. And if we do a bit of algebra, we'll end up like this. For those who want to go through the algebra, because it is something that you may be asked to do in an exam, it would run something like this. 1 plus j omega cr plus j omega squared times LC equals 1 plus j omega over the first pole times 1 plus j omega divided by the second pole. Multiply these brackets out. 1 plus j omega, 1 over p1 plus 1 over p2 plus j omega squared divided by p1, p2. Equate coefficients of j omega. and we see that 1 over P1 plus 1 over P2 equals CR. We can also see that LC is 1 over P1, P2 by equating the coefficients of j omega squared. Gives us 1 over P1, P2 equals LC. And that gives us that 1 over P1, or let's say 1 over P2, equals P1 times LC. I can substitute this back into here and end up with 1 over P1 plus P1 LC equals CR. Multiply every term by P1 and move the CR over here, and we would end up with P1 squared times LC minus P1 times CR plus 1 equals 0. That's a quadratic expression in one of the poles. It has two roots. The two poles that we would get, the two roots that we would get out of this quadratic are the two poles that we're interested in up here. And standard quadratic equation, CR plus or minus the square root of, in this case, CR all squared minus 4 times LC times 1 divided by 2LC. That's the frequencies of the two poles. Right, you can write that in a slightly neater way by dividing through, by LC on both the top and the bottom, and we end up with this expression here for the two poles. Right, this, you will notice, does raise the possibility of complex poles. In the case where R over LC, this term here, is bigger than this term here, then we end up taking the square root of a negative number, and that will result in complex poles, which is where things get a bit interesting. Solving quadratic equations like that all the time, when you want to know how a second order system behaves, can get a bit tiresome, so there is an alternative way of doing it. The alternative way is, rather than work out the frequencies of the two poles, specify the behavior of the second order system in terms of two other factors known as the resonant frequency and the Q factor, or quality factor. And these are defined by writing the denominator not in terms of 1 plus j omega over P1 times 1 plus j omega over P2, but in terms of this standard form here, where the resonant frequency is omega naught and the Q factor is Q. So if we go back to look at the circuit we're analysing here, this one, the denominator is 1 plus j omega CR plus j omega squared LC. The standard form for the response in terms of the resonant frequency and the Q factor is this. So, to work out what Q and omega naught are in terms of the parameters of the circuit, we just have to equate these two expressions. This one that we got from the potential divider equation, and this is the general form for expressing a second order response in terms of a resonant frequency and a Q factor. Well, quite clearly, Q times omega naught must be 1 over CR, and omega naught squared is 1 over LC, which means that Q must be 1 over CR times omega naught, and omega naught is the square root of 1 over LC, so I could write it like that, and that's just the square root of L divided by the square root of C and a 1 over R on the outside like that. So we have an expression for our resonant frequency in terms of the inductance and the capacitance in this circuit, and an expression for the Q factor in terms of the inductance, the capacitance, and the resistance of the circuit. Note that the resonant frequency is not a function of the resistance. We'll come back to that later. Before we go on, it's worth thinking a little bit about what the physical meaning of these two new parameters are. What does the resonant frequency actually mean, and the Q factor actually mean, in terms of the response of these circuits? Well, the resonant frequency first. The resonant frequency is the product of the roots of the quadratic equation, which means that it's the product of the two pole frequencies. We could write P1 times P2 equals omega naught squared. It's also the frequency where the impedance of the capacitor and the inductor cancel out. If you remember, the impedance of an inductor, J omega L, the impedance of a capacitor, 1 over J omega C. So if we have a network like we do here, with a resistor, an inductance, and a capacitance in series, the total impedance of the inductor and the capacitor in series is the impedance of the inductor plus the impedance of the capacitor. And at one particular frequency, that's going to be 0. And that occurs where J omega L equals minus 1 over J omega C. This happens because I can multiply the top and bottom of this by J. That would give me minus J over J squared omega C. But J squared is minus 1. Those two minuses cancel. These J's cancel. And we end up with omega L equals 1 over omega C, or omega equals 1, omega squared rather, equals 1 over LC. And at that frequency, and only that frequency, the net effect of the inductor and the capacitor in series is 0. So that's the resonant frequency, the frequency where the inductance and the capacitance cancel out. Now, the Q factor is the resonant frequency divided by the sum of the roots, if you go through the algebra. But more interestingly, for this circuit, the Q factor is the gain at the resonant frequency. Quite a simple bit of algebra to work this out. If you just put omega equals omega naught in the general expression, we get 1 plus j omega over q omega naught plus j omega squared over omega naught squared here. These two omega naughts cancel. J squared is minus 1. The plus 1 and the minus 1 cancel out. That just leaves us with 1 over j omega naught over q omega naught. The two omega naughts cancel. That just ends up with this. And the magnitude of this, that's h of omega naught, is just equal to the magnitude of minus jq, and that's just q. We have this. And that's probably the easiest way to think about Q. Q, for this circuit, a series RLC, is the magnitude of H at the resonant frequency, the magnitude of the voltage gain at the resonant frequency. Right, that's about all that will fit in one YouTube video, so I'll stop there and carry on in the next one.